the online audience and all the participants in Trento. So it's my pleasure to introduce Thomas Du from the Universität Bonn and the Forschungszentrum Jülich to talk about using machine learning to alleviate the sine problem in the Hubbard model.
Thank you very much. Let me first start off by thanking the organizers for inviting me, or more importantly, for not forgetting me. With regards to this workshop, I'm very excited to give a talk here. And I really wish I could actually be there in person, but my wife would not let me go for good reasons. So to start off, I would like to acknowledge my collaborators in this effort, if anything, to at least share the blame for the work that we've done. A lot of this work was initiated by a former PhD student of mine. His name is Jan Lucas Wienen. He's since graduated and he's gainfully employed in Copenhagen. But the results that I show in the first half of my talk are based off of his thesis. Since he's graduated, we've had two other PhD students join the group, and they've more or less taken over this effort, Marcel and Christoph here. And the results that I show in the latter half of the talk are based off of their more recent results related to this effort. And of course, there is Evan Berkowitz, who is a staff member at the Forschungszentrum. He's been a longstanding collaborator of this project. And of course, I would like to also say thanks to the various other members of our research group at the Forschungszentrum. So I want to talk about a particular type of sine problem. Yesterday, we heard from Will Detmold, one form of a sine problem. My sine problem that I want to address is a little bit different. It's related to the case when the action has an imaginary component. I think most of this is old news for most of you already, but let me just, give you a little bit of an introduction so that we can give some perspective here. So, like usual, I want to calculate the ground state expectation value of some operator O. And I do this in a path integral formalism. I integrate the operator O weighted by some exponential of some minus action here. And as long as the action is real, then this quantity here, e to the minus s phi divided by the partition function, can be interpreted as a probability density. And because our system tends to be high dimensional, we estimate this integral stochastically. Okay, we use lattice stochastic methods to come up with an estimate for this operator or observable here. That's all fine and dandy when like I said, when the action is real, but there are cases where the action has an imaginary component as well. And when this happens, one can no longer interpret this probability density in any meaningful way because it is no longer positive definite. Okay. And so this raises the question of how do we interpret such probabilities, and it is a serious problem when it comes to lattice stochastic methods. More generally, this is known as the complex phase sine problem. And where does this sine problem show up? Well, it's quite ubiquitous, believe it or not, as most of you know. I mean, straight off the bat, we know that life in Minkowski space suffers from this particular sine problem. And that's probably the main reason why we go to imaginary time and work in with Euclidean time. Just as important or interesting is the case of finite density QCD, zero temperature finite density QCD, right? We turn on a chemical potential for the quarks or equivalently a baryon chemical potential. This induces a sine problem, and because of this precludes us from answering questions, very interesting questions related to the phases of quark matter and high density. Such questions and their answers have relevance to compact astrophysical systems in the universe, like neutron stars and supernova. And it may very well be that the Lagrangian itself, even after Wick rotation, has terms that are still induce a imaginary term in the imaginary phase. For example, the QCD theta term, which we heard about from Borum's talk a couple of days ago. And there are numerous other examples that are not particularly even related to lattice gauge theories, but for example, in nuclear lattice effective field theory, where we do lattice stochastic calculations using nuclei as degrees of freedom. When you go to neutron-rich systems away from the drip line, they also suffer from a sign problem as well. So I want, so the sign problem is really quite ubiquitous. I actually even want to be so bold as to say it shows up in the most interesting problems in particle and nuclear physics. Okay, obviously that's a very subjective statement, but I'm trying to be a little bit provocative here. But it's not unique to particle physics, the sign problem, and I dare say, I will also say that our condensed matter colleagues also suffer in our pain as well when they look at their systems, particularly systems that represent high density and strongly correlated electrons. Okay, when they want to do stochastic simulations of doped systems, again, systems with a chemical potential, but in this case, an electron chemical potential, they immediately suffer a sign problem just like we do in high density QCD. And perhaps even more interestingly, because of the crystalline nature of some of these systems, these condensed matter systems, the geometry of the crystal itself can induce a sign problem as well. This is probably something that we don't see much in particle physics because we use a particular discretization that is quite nice. But in condensed matter physics, one is not always free to do that because of the specific geometry and symmetries of the system in question. And I'll actually give examples of both these types of systems that have a sign problem, that induce a sign problem. Now, my talk is not going to be particular to particle physics, but I hope that the type of things that I discuss have analogs in particle physics. I will be mostly concentrating on yet another system in condensed matter, but at least it's not the Ising or X-Wire Potts, but in this case, it's the Hubbard model. I'm going to be talking about the Hubbard model on various low-dimensional geometries here. And so the Hubbard model, for those who have forgotten, it's basically a collection of three terms. The first term is the dynamical term, where we have creation and annihilation operators coupled by some connectivity matrix kappa. Okay, we have an on-site interaction U, and we have a chemical potential that gives a bias of one fermion species over another. The n's and n tildes here represent number density operators for the different fermion species here. Okay, so A and B are creation and annihilation operators for different fermion species. And so for this particular problem, you can think of the fermion species, the two different ones for spin up or spin down, or what we usually do is we interpret them as particles and holes. Okay, and as you might expect, we're interested in calculating expectation values of some observable O weighted by this partition function Z here. Okay, and the partition function I write here, I introduce beta, which is an inverse temperature. And the trace here means a trace over the entire Fock space of the system here. Now, as is written here, is not amenable to lattice stochastic methods. So to do that, I want to transform this partition function into a path integral. Okay, and there are various ways to do that. You can look at some of these references here to figure out how to do that, but it's relatively straightforward to convert the partition function into a functional integral over some auxiliary field phi, where the kernel of that integration has a Gaussian in phi squared, the auxiliary field. And not surprisingly, there is a determinant of a product of two matrices M. So these are fermion matrices. Now I use M to represent my fermion matrices. In previous talks, you've seen D or D slash. Again, it's the same, more or less the same principle here. The reason why we have two fermion matrices is because we have two different fermion species here. Okay, so I'm hoping this actually looks somewhat familiar to lattice gauge theory, right? We have the same thing in QCD. We have a product of fermion matrices for the different flavors. And we have, say, if you will, a gauge part of the action here. In our case, the gauge part is quite simple. It's a Gaussian. The field itself is not dynamical. It's just an auxiliary field that came about from a Hubbard-Swiatovich transformation to simplify this quartet coupling. It's the same transformation that we heard about from Andre's talk yesterday as well. So And as usual, we couple everything here to define an action S. Fine. So it's very similar to what we find in Lattice QCD, except the group manifold is obviously much more complicated than in this case. Now, a couple of things I want to say about this, the form that I've written here. If you notice, the integration we do over the auxiliary field, the fields are all real, okay? And that means then that the gauge part, if you will, the Gaussian part, is positive definite, always. So if a sine problem is going to show up, it's going to be because of the determinant of the fermion matrices here, okay? And it turns out that yes, depending on the system we're looking at, the parameters and the geometry, there may be configurations of phi such that the determinant actually becomes complex, okay? And therefore we have a sine problem. Also important is that there may be configurations of phi where the determinant vanishes, okay? And this is a very interesting feature of related to the inclusion of fermions in our theory. So when the determinant vanishes, that means that the kernel goes to 0, obviously, or equivalently, the action S here goes to infinity, okay? And I just bring this up now because you'll see examples of this in a moment here. So I would like to discuss a little bit more in depth of how the determinant here, those fermion matrices, can actually induce a sine problem. And it turns out that, obviously we know that turning on a chemical potential can induce a sine problem. And this is particularly so when we look at systems whose lattices are what's called bipartite. So when we have bipartite lattices, that means that all nearest neighbors can be colored oppositely. So we can use two colors to label our lattices, and every nearest neighbor has the opposite color. The standard square lattice is bipartite. What we use in Lattice QCD is bipartite. Something that's very interesting in condensed matter is the Honeycomb lattice. It is also bipartite, and the Honeycomb lattice has many interesting applications, for example, graphene and so forth. Interesting feature of the bipartite lattice is that if you had no chemical potential, if it was 0, it turns out that the fermion matrix, the second fermion matrix, the second species here is equal to the dagger of the first fermion species, which means that dagger is always positive definite. And so such a system there at 0 chemical potential is really amenable to lattice stochastic calculations. And this is what we do when we try to simulate, graphene, large scale graphene and so forth. But as soon as you turn on a non-zero chemical potential, all bets are off. The determinant can be complex, okay? And a sine problem shows up, no surprise. But what's also very interesting in these low dimensional condensed matter systems is that, like I said before, the geometry plays a role as well. Even if you had 0 chemical potential, if you have a non-bipartite lattice with interactions, for example, C60 here, which is an American soccer ball or Fußball, as we say here in Germany, the presence of these pentagons, and there have to be 12 pentagons here, makes this geometry non-bipartite. The pentagon is, you can quickly convince yourself, cannot be colored in 2 colors. It needs at least 3 colors. And so it's non-bipartite. And just that geometry itself is sufficient to induce a sine problem, okay? As soon as you turn on interactions, independent of chemical potential. So we're going to consider examples of both here in my talk. And we're going to try to understand how we can alleviate the sine problem in both cases here. But before I go into detail about how we do this, I should say that, I should say obviously that the sine problem is not a new phenomenon that we have to tackle. It's been around since the beginning of time. And there are many different methods that have been developed to try to tackle the sine problem, okay? And I want to just list, probably the more famous ones, just to give a little bit more perspective, and then you'll see how our method potentially differs from these other methods here. But, when presented with the sine problem, probably the first thing that anyone would do to address the sine problem is to do some type of reweighting, Okay, so reweighting is quite simple to understand. You want to calculate some expectation value, some observable in the presence of an imaginary action or an action that has a complex phase. What one does is one reweights that observable with that phase, and one calculates the expectation value using the real part of their action as a distribution. Now, that's not the original observable that we're trying to calculate. To get back to the observable that we're trying to calculate, we have to then divide by the expectation value of the phase itself, okay? And so this is a purely formal expression. The utility or applicability of that depends on how severe the sine problem is. And when I say severe, what I really mean is what the expectation value of this phase is. And this is something I call the statistical power. I use this numerous times later in my talk. So as you might imagine, if there is no sine problem, in other words, if the phase is 0, then this guy is just 1, and the expectation value of the statistical power is 1. That is the best world to live in, no sine problem whatsoever. But if the fluctuations of the phase are quite severe, very, very severe, then the expectation value here goes to 0. Okay, this expression is still formally correct, but if you're trying to obtain a stochastic estimate of this operator in the presence of some term that is stochastically consistent with 0, you can see then why reweighting fails in this case. Okay, it just fails. Okay, so reweighting is not a general solution for everything. Sometimes the culprit, the term that causes the sine problem, is actually a small quantity. And if that's the case, then you might be able to just do simple expansions in that quantity. For example, if the baryon chemical potential is small, you might imagine just expanding the action in that term, and then calculating moments of that term. Okay. Another example, which we already discussed about, was the QCD theta term. That's also, we know experimentally, is small. And we can use that fact to do perturbative calculations in theta. The coefficients of these terms have to be calculated non-perturbatively, but they don't suffer any sign problem because we've done an expansion in the term that causes the sign problem. A little bit more description you can find in one of our recent papers here by Jack and myself and others, if you're interested. Or you could take the term that's causing the problem and just analytically continue it into the imaginary plane, just very similar to what we do with imaginary time. The issue here is then, once you do your calculation, how do you analytically continue back to the real plane? Okay, there are issues about how one does that, and it's, I think, an open-ended question. And of course, people, I'm sure, have heard about complex Langevin methods here using stochastic quantization. It's not really Monte Carlo sampling. It works great when it does, but then when it's wrong, it's really wrong. And it's hard to know the demarcation when it does work and when it doesn't work, okay? More recently, people have considered using tensor networks. I won't say anything specific about it, but other than the fact that tensor networks are deterministic calculations, they're not stochastic. And so because of that, they don't care whether or not there's a complex term in the action or not. Okay, so they are immune to the sign problem. They work extremely well for low D systems, particularly D equals 1 systems. But I would say that, you know, the memory requirements, even the scaling as you go to larger dimensions, are quite harsh or can be very difficult here. So I think the verdict is still out with regards to tensor networks about what type of systems one can push this to. But you know, that hasn't prevented us from trying to investigate such systems here. If you're interested, you can look at this paper here has been recently accepted about using tensor networks to simulate the Hubbard model as well. The method we use instead is it's called Leftjust thimbles. Now, this has already been mentioned a couple times in various contexts in previous talks. It's based off of holomorphic flow, very similar to what we heard from Will Detmold's talk yesterday. And that's the method we use here. And I'm going to go into detail with that, describe that more in a moment. But I really want to point out something here. So, you know, the method we choose, we are not going to solve the sign problem. Okay, obviously not. The sign problem, the general sign problem, is an NP hard problem. I'm not going to solve it. The goal of using holomorphic flow is instead to alleviate the sign problem, and to alleviate it enough such that reweighting can take over and provide reliable estimates. How we alleviate the sign problem basically is the following. What we want to do with our method, which I'll describe in a moment, is basically make the statistical power as large as possible. Okay, so that is the philosophy behind our method. And hopefully by the end of this talk, I will have convinced you that this philosophy works. Okay, so Leftjust symbol primer. So the theory of Leftjust symbols is, I think, can be somewhat complicated. But a description of it doesn't need to be complicated. Perhaps most of you have heard about it already. I just will give a very simple example in one dimensions to illuminate or to enumerate the main features of Leftjust symbols and why they are useful when it comes to the sine problem. Okay, so the 1D example I want to consider is the following action here. Okay, so this is just some action I made up. It has, if you will, a gauge part, a quadratic part, and it has a logarithm as well. And this logarithm I inserted here, so because I wanted it to mimic particular features that we find when we deal with fermions. Okay, and I'll explain more about what I mean here. So the whole premise behind Leftjust symbols is similar to what we heard yesterday. The idea is that we want to first consider the following integral of the line integral of phi of e to the minus s here with this action here. And so originally the integral is on the real plane, or in this case, since it's one dimensional, it's just along this dashed line here. Okay, and because our function is holomorphic and so forth, we are actually free, due to Cauchy's theorem, to actually deform our line integral into the complex plane. Okay, just like Will and others discussed yesterday. But in this case, we want to deform them to particular curves or manifolds in the complex plane. And these manifolds are called Leftjust symbols, and I'm drawing them here. So this curve here, all these curves are Leftjust symbols, as a matter of fact. This is one here, this is one here, and this is another one here, and so forth. These are Leftjust symbols in the complex plane. And these symbols are defined in the following manner. Each symbol has its associated critical point where the gradient or the derivative respect of phi vanishes. That's shown by these blue points here and here. And the symbols are defined by the collection of all points such that when you flow them with this flow equation here, when you numerically integrate the flow equations, you will asymptotically approach these critical points. So this is what's represented by these lines here. So all these points here, if you flow with this flow equation, they would approach this, asymptotically approach this critical point. Same here, and same going here and here. So those are actually the definitions of the symbols themselves. What you also see here is that there are points where the action blows up because of this logarithmic term, and those are represented by these red points here. And these red points are actually interesting because they allow symbols to connect to each other, or they all go to these red points. This is one symbol, and this is another symbol here, for example. Now, why are these symbols interesting? Like Will mentioned yesterday, and Andre mentioned yesterday, you are free to deform your integration in any way you want, as long as you preserve the homology class. You're guaranteed to keep the same integral. The symbols are interesting because if you move along this particular curve, the imaginary part of the action on this curve stays constant. Okay, and so that's actually quite interesting from a stochastic point of view. This means then that this integral is equivalent to the sum of all symbols where you integrate along the curve here on the symbol here. Okay, and because the action is constant, because the imaginary part of the action is constant on these symbols, you can just factor that imaginary part out. And the only thing you have left is the integral over the real part of the action, which is positive definite. So in this case, you can see how this method can potentially solve the sine problem for you. Okay, so I went over this relatively quickly, but let me try to explain, use some figures to give you an idea what's going on. So the original integral was along the real plane here. Okay, and if I plotted out the real part of the action on this real plane, this is what the real part looks like. And then the imaginary part is down here, and it's not zero in this case. And it's moving around, it's fluctuating. I can then deform my integration onto this symbol here plus this thimble plus this thimble here. And when I do that, then what I find then is if I trace out the real part of the action here, it looks something like this, and it diverges here because you hit this red point. It diverges here as well because you come back and hit this red point, and so on. But more importantly is that the imaginary part of the action, if you look now, is completely constant on each of these thimbles. Okay. So that's quite nice this in principle solves the sine problem. And for this one-dimensional problem, it's actually very simple for us to determine all the critical points, all the Leftjust thimbles, and so forth. And it's actually quite easy for us to actually plot what these thimbles look like. In reality, when we go to more realistic systems with larger dimensions, these curves become high-dimensional manifolds, okay, in space. And so, and so later when I show other plots, it's very difficult for me to represent high-dimensional manifolds, right? So I have to do some type of projection down to a 2D plane so that I can show some type of plots. And what I usually do in these high-dimensional cases is that I take the average value of phi, of configuration phi, and I take the real part. Or I take the average value of phi and I take the imaginary part to actually project down to something in which I can make figures. Okay, so making figures of high-dimensional manifolds is not easy. It's actually an inconvenience, but that actually is not the real issue with regards to Leftjust thimbles. When we go to high-dimensional systems, the problem with Leftjust thimbles is we don't know a priori where they are, okay? It's not trivial to find all the critical points, and then from that, determine the thimbles themselves to do the integration on. Actually, I think to determine that, all the thimbles and their critical points is just as hard as the original sine problem itself. Okay, so that's actually a problem. That's one of the drawbacks of Leftjust thimbles, but that's okay, because if you remember, I'm not trying to solve the sine problem, I'm trying to alleviate the sine problem. And the way we do that is in the following way. We can approximate the thimbles by applying the flow equations and flowing them in a clever way. Okay, and by flowing them, one actually can asymptotically approach these thimbles or make better approximations to the thimbles. Okay, and these are the flow equations that I use. This is not so different from the gradient flow or Wilson flow in Lattice QCD. There's a complex conjugation that makes a big difference, but the principles are the same. We are flowing in some extra flow time dimension here. Using the heat equation, if you will. Well, for gradient flow in Lattice QCD, we use the heat equation. Okay, so the idea is the following: we take any configuration on the real plane, we integrate this differential equation and a fixed finite flow amount. At the end, we come up with a new contour that, for example, with a fixed flow time represented by this orange figure here, orange curve here. And this flow should be a better approximation to the actual thimbles themselves, okay? If we flow even longer, we would then have another manifold or another curve, this brown curve here, for example. There are issues when we have fermions, how far we can flow and so forth. I won't go into that, but that fermions do represent a problem. They basically, these points here represent attractors to the theory. And so the amount of flow you can do is not infinite. But that's something one has to take care of. But the goal here, again, is that if using these flow equations and flowing, we can have a better approximation of the thimble. And hopefully, by having a better approximation, the sine problem has been alleviated, and hopefully alleviated enough such that reweighting can take over. Okay, and this is known as a generalized thimble approach. Many people have considered this in the past, and this is what we do as well. Okay. Of course, this raises the question, how does one, oh, sorry, I jumped ahead. That is the more general approach for the generalized thimble to flow, but there is an even simpler flow that one can consider. This is something very similar to what Will talked about yesterday. One can just take a constant contour deformation, okay? Just like he did yesterday. However, one difference between his method and ours is that, in Will's method yesterday, how much he the constant he chose to deform, to do the offset, was determined by some minimization process. In our case, we always choose our constant deformation to intersect this thimble, what's called the main critical point of the main thimble here. Okay, so in all the problems that we've considered, it turns out there is one critical point that is actually quite relatively easy to determine. It's this, what's known as the main critical point. It's the critical point of the symmetric thimble, the main thimble here. And so we do an automatic shift all the way up to this point here. And this is what we call the tangent plane. And again, this constant shift still respects the homology class. One expects then to get the same observables as if one had done the integration on the real plane here. Okay, so in my results that I show later, I'll be showing results with the with flow using a neural network, as well as calculations from the real plane and calculations from the tangent plane to compare all these different methods here. Okay, so given these manifolds, how do we actually sample from the manifolds? Because ultimately, in the end, I want to do a stochastic sampling. Okay, and so if you have a manifold or an approximation of the manifold, this is the term that we want to integrate for one of the thimbles, for example. var phi here, it represents integration of fields on this manifold. So this integration is actually on a curved manifold here. That's actually quite difficult for us to do. And so what we do then is we do a change of variables back to, if you will, the real plane. Phi here sits on the real plane. Okay, that change of variables goes back to the real plane. Of course, we want to evaluate the observables and the actions on the manifold still. So var phi becomes a function of the variables on the real plane. And then, of course, since we've done this change of variables, we induce a Jacobian det J of var phi here. Again, we saw this yesterday in both Will's and Andre's talk. And so in the end, the sampling that we do is, yes, we move around on the real plane, but we want to then generate ensembles with weights determined by this S effective action that involves the action on the manifold minus the log det of the Jacobian here. And I highlight this because this log det J is a problem for us. You can imagine doing a constant shift. And in that case, the det J is just 1 and the log vanishes. That's a great simplification of the tangent plane. But in principle, if you have some curved manifold and so forth that you're trying to do integration on, this log det J is not trivial to calculate. And so we'll come back to this in a moment. So this basically tells us how we try to incorporate then the holomorphic flow in our stochastic calculations. The idea is the following: we take some location on the real plane, phi and its conjugate momentum, and we do HMC on the real plane to make a proposal from phi p phi to p prime phi prime. Okay. Once we've made that proposal, we then use the flow equations to flow up close to the manifold to obtain var phi. And then we accept then with the effective action in this manner here. Okay. There are intricate issues related to ergodicity and so forth, but if you try to take care of these things, one can actually show that this procedure is completely reversible because the flow equations are invertible and it's reversible and therefore satisfies detailed balance. And this is the method we choose here. It's actually quite simple. We take our HMC. The only difference is that every time before we do an accept reject, we have to flow up close to the manifold, and we have to remember what the action was on the manifold prior to doing the HMC step so that we can do the accept reject. I should say that there have been methods to actually do HMC directly on the curved manifold, although I think such calculations tend to be very, very tedious and very, very complicated. But this is the formalism that we choose here. And we've applied it to a very simple problem, a three-side problem with the Hubbard model. Now, the three-side problem is non-bipartite, and so therefore it suffers immediately from a sine problem one of the worst sine problems you can have as soon as you turn on interactions. And the principle, but the principle is the same. We take any configuration on the real plane that was proposed by HMC. We then flow it with these flow equations by a certain amount that gets us more or less closer to the thimbles. And then we do accept reject, and we repeat this step here. And what we find then is that when we do HMC on these thimbles, or approximations of the thimbles, the real part of phi takes on these the distributions here, coming from the troughs here in the Leftjust thimbles. And probably more importantly, the phase, the imaginary part of the action, takes on these peak distributions here as well. And these little peaks here represent then the different thimbles that we are sampling from, okay? And when we try to calculate correlators, okay, and observable in this case, so in a correlator, I don't think we've mentioned this in the past, but the correlator is just the expectation value of a dagger separated in time t. It gives us information about the interacting spectrum of the system. If I had done the problem using the original real plane, just vanilla HMC, the sine problem is actually severe enough that I cannot get the correct answer. Okay, and the correct answer in this case is given by the black line. It's a three-side problem. We can actually solve it exactly. Okay, but if I use the thimble, if I flow up, you can see that I get the results, the red points agree much, much better with the exact results here. And if you compare the statistical power of the thimble calculation, the statistical power here is around 0.8. It's not 1, but still it's not bad. It's actually pretty good, actually. And if you were to calculate the statistical power using just the original real plane calculation, vanilla HMC, you see here that the statistical power is an order of magnitude smaller. It's really bad. And there are no peak distributions anymore. It's just basically the distribution of the imaginary part from negative pi to pi is just almost flat. Okay, and that's a sign of a severe sine problem, wildly oscillating in this case. And so it does seem to work. It seems like we've come up with a method that we could use. Life is great, right? Well, unfortunately, no. The problem I showed here was a three-side problem. It was so small that we can actually do the flow directly, numerically, and so forth. But in general, when we try to go to bigger systems, it's just numerically not viable. The problem will not scale sufficiently for us. The reason being is, as you might imagine, the numerical flowing of the fields is not cheap. It's not that expensive, but it's still not cheap. And it's actually, you know, as you get to bigger systems, there will be demands on doing this type of flow. But probably even more severe, well, definitely even more severe, is the calculation of the Jacobian, the induced Jacobian in this case, and trying to determine this Jacobian directly from the flow equations is an extremely time-consuming problem. It is way too complex to do. And as soon as we try to move to a four-side problem with this method, it just took too long to do this problem. Okay, so we need a better way to try to approximate these thimbles and its Jacobians, or a much more efficient or fast way to do that. And this is where machine learning came in and helped us, okay? And these ideas were inspired by Andre and others as well, okay? So the idea then is that we would like to train our network in such a way that we feed in configurations on the real plane, and what it outputs are the values of the imaginary parts that bring us up to the manifold, the Leftjust symbol, okay? And so that's relatively, that is our idea, and this has been proposed many years in the past, and if you do this, this is what people call the learning fold, which you've heard about from in mention in Andre's talk yesterday and Will's talk as well. So how we do this training is by basically, we generate a training set of data. And the training set is determined by just randomly sampling configurations. We use a Gaussian sampling of configurations on the real plane. And then we actually flow it up using the numerical flow equations up a certain amount. And that is represented by these blue points here. And we train our network such that, you know, such that when we feed in red points for initial points, it outputs then the blue points of the training set here. Okay, and we don't do anything fancy. We have one hidden layer. We use a softmax activation function. We do, in this case, we use an L2 loss function. And this is your classic example of supervised training. It's each layer, the hidden layer is densely connected as well. And what we found is that it actually trained relatively well. We were able to train it well. Now, once we had the network trained, we had to now incorporate that back into our HMC routine, or our stochastic calculation. And that was actually straightforward to do. This slide should look very similar to what I showed a couple slides before. Again, we do the proposal using standard HMC, but instead of flowing from the real plane up to the manifold, we feed it through the neural network, and that gives us then its approximation to the manifold. And then we do accept, reject, and so forth. And again, because the network we use is invertible, in principle, this process is reversible, and it should satisfy detailed balance as well. Okay. And what we found in this case was that for some systems, it was clear that the neural network outperformed the original vanilla HMC. Okay, and so I'm again showing another non-bipartite system. In this case, the tetrahedron with these parameters here. In the top row, I'm showing standard HMC on the real plane with reweighting, and on the bottom row, I'm showing HMC with our neural network approximating these complex manifolds. And as you go from left to right, the difference is just the number of measurements that we use to obtain our estimate. We go from 1,000 measurements all the way up to 1,000,000 measurements here. Okay. And because the system is still relatively small, 4 sites, we can calculate the exact results for the correlators. That's these black lines here. And you can see that for standard HMC, the sine problem is just too severe. Even by 1,000,000 samples, we cannot reproduce the exact result here at all. Okay. However, once we have a trained network and we incorporate it into our calculation, you see that as we increase the sampling, it converges very nicely to the exact result. Okay. And so this gives us a lot of confidence that this formalism that we're using is useful. It can be used to calculate systems that have a severe sine problem. We've also looked at systems that are bipartite but have a non-zero chemical potential. And here's an example of the statistical power, the mean expectation value of that phase as a function of mu for what I call a 4-site honeycomb lattice. So 4-site meaning that these guys here are the physical lattice, and because of periodic boundary conditions, the image part ions form then this graphene lattice. And what's interesting to see is you can see here that the statistical power, if you were to do lattice calculations just on the real plane, vanilla HMC, the statistical power drops like a rock and goes basically to 0 by the time you get to mu equals 2. Okay, so simulations out here just won't get you anywhere. The tangent plane actually does okay for many points. It's actually, it does go down to less than 0.2, but it doesn't go to 0. And perhaps more interestingly, as you get to very large mu, it goes back up to 1, things asymptote to 1. And the neural network, where we train by flowing a little bit above the tangent plane, does even better. It has a statistical power that hovers above around 0.7 and above here. And such statistical powers we found in the past are very sufficient to calculate observables here. Okay, and so that's actually quite interesting what we found as for such a system as a function of chemical potential mu. And so we can then look at correlators again. Correlators are one of our favorite observables to calculate. And so on the left plot here, I'm showing the exact results in black, the real plane HMC in orange, I hope you can see that, and the tangent plane HMC in red. And aside from the low energy correlator here, the real plane HMC just fails. It's just noisy and it doesn't even fall on the line at all. Tangent plane, if you look closely, does okay. It doesn't do so bad here until you get out to here. We can compare now the tangent plane calculation with the neural network here, and that's what's shown on the right. So the tangent plane is again in red. It should be exactly the same as what you saw on the left here, but now superimposed on the results are the neural network as well. And the neural network does even a little bit better in this case. And perhaps out here, you can definitely see here, it does do better here as well a little bit. Although at short times, you can't see a difference between the tangent plane and the neural network. Okay, so this is actually quite nice for us. The agreement that we get between the neural network and the exact results are very nice here. Okay, within uncertainties, they line up with the exact results. You might actually ask, why even do neural network? Just do the tangent plane, because the tangent plane works as well. But here I give an example where even the tangent plane is not sufficient. Okay, and it fails.
Thomas, we need to go to get to an end soon.
Yes, I'm going to get to an end very soon here. Thank you very much. Okay, so finally, then what we have then is an example for 18 sites, Honeycomb lattice. And in this case, the tangent plane, which is blue, does very well with regards to the uncertainties, whereas the tangent plane has failed in terms of because the uncertainties are extremely large. Okay, and in this case, the system is so large we cannot actually calculate exact results. So the results we have here represent predictions then for the 18-site Honeycomb lattice. And we've also calculated other observables like the charge density as a function of chemical potential as well. I won't go into detail there, but I just wanted to come back to the issue of this determinant of J. Okay, and currently up to now, our transformation that we use is one where we take the real part of the configuration and we feed it into a neural network, and the neural network returns back then an imaginary part that gets us up into the complex plane. And this particular type of transformation was motivated by various reasons. I won't go into that, but the determinant of such a transformation is one where is represented by 1 plus the Jacobian of the neural network. And this particular form of the Jacobian, because of this 1 plus here, there's nothing we can do to it to actually make it scale favorably. It will scale with order volume cube. That's one of the restrictions of this particular type of neural network. Okay, and it's the reason why it's hard for us to push to very, very large systems. So recently we've come back and we instead considered what we call a complex valued neural network. So please don't confuse this with convolution neural network. This is complex valued neural network. And what this means is that we generated a neural network where the inputs are actually complex values. Okay, they live in the complex, they are complex numbers. The biases and weights themselves are also complex as well. Okay, and this type of neural network that we use, where we take in phi and what it returns back is then the manifold, directly the manifold phi, which is complex. It allows us to write the Jacobian directly as the product of the Jacobians of the various layers themselves. And here you can then use these clever affine couplings that we heard about from yesterday's first talk, for example. And in so doing, we can actually find a coupling that has a Jacobian that scales very favorably in the volume. And I'll go through this quickly. We heard about this already from yesterday's first talk. The type of affine coupling layer we do is one where we only vary half our inputs at every coupling. We take phi, we split it into two parts, randomly, if you will, phi A and phi B. Phi A doesn't change, it stays the same, but phi B changes, and it changes depending on what phi A was as well as phi B. Okay, and then we do it again, but we alter what we change. In this case, phi B stays the same, but phi A changes depending on what phi B is and so forth. Okay, and we do this alternating back and forth. The coupling layer, we can choose whatever we want. We use a linear coupling layer, for example, and we can repeat this many times. And this is what we use then for our complex valued neural network here. And the nice thing about this Jacobian, the Jacobian of such a system, as we saw yesterday, it's triangular. In this case, it's lower triangular. In this case here, it's upper triangular, and so on. And when we try to calculate the determinant of J, And because they're triangular, what we find in the end is it's just a product of the diagonal elements of all these triangular matrices. And what we have then is a calculation that is order volume times the number of layers that we use. And again, this was inspired by work that we heard about yesterday and so forth as well. And second to last slide, we tried this. We recently did this on the simplest problem, the two-site model. We had two affine layers that did this coupling in this manner here. We were able to train. And what we found was very promising. We were able to reproduce the exact correlators very well. And here are the imaginary, here's the distribution of the phase. We find these peaks that represent then the various manifolds that we're trying to sample. Okay, so finally, I just want to conclude then. Thank you very much. So I've talked about the Hubbard model and its sine problem and how we try to alleviate it with holomorphic flow. We developed a complex valued neural network that really allows us to get a determinant J that scales as order volume. And this is a game changer for us. This will allow us to push to much, much larger systems like C20, C60, dope graphene and tubes as well. Ultimately, believe it or not, we want to apply this to lattice gauge theories. And the takeaway message I want to say here is that, a lot of the studies up to now have not really included fermions. From our experience, fermions are going to make the system much more challenging and at the same time, much, much more interesting to look at. Thank you very much for your time. I'll take any questions now.
Thanks a lot. Thanks, Thomas, for this nice talk. Are there any questions? Okay, Kai, can you unmute?
Yeah, so maybe I have a naive question that, so for your trained neural network, can that generally solve the flow equations for any setup, or it's only can be applied for that specific setup, depending on your training data set?
Yeah, very good question. So unfortunately, the manifolds depend on, yes, the particular parameters that you choose, in particular, the on-site coupling, the geometry of the system, the chemical potential, as well as the number of time slices. So it does depend on that. So if you have a different geometry, a different system, you have to train a new manifold. But the important thing here is that once you've trained it, then you can calculate any observables you want. So with that same system. So we're not dependent on the observable, but we are dependent on the system as well, the specifics of the system. Yes, excellent question.
Okay, thank you.
Okay, I need to cut you off before there are any more questions occurring. Thank you again for the very nice talk.